Hi, everyone. Welcome to the Optimizing Long Duration Park Orbit for Earth Escape Trajectories, our Q4 webinar, which is hosted by AI Solutions and our Space Products team. I'm your moderator, Danny Brown, Space Products Account Executive here at AI Solutions. I'm also joined by Chris Ulrich, also a Space Products Account Executive, and he will be monitoring your questions during and at the end of this webinar. So make sure you stick around for that. We have a very exciting presentation for everyone today, led by our very own Justin Hartland, where he'll be taking us through his research and examples for long duration park orbits. Justin is a flight design engineer working with NASA's Launch Services Program at Kennedy Space Center through AI Solutions. Justin was an AI Solutions intern supporting LSP in the summers of 2023 and 2024. He graduated in May 2025 from Embry-Riddle with a bachelor's in aerospace engineering and started full-time with us right after that. His work focuses on launch vehicle trajectory design and optimization, supporting NASA's launch services contracts. Now, without further delay, I'll turn it over to Justin. Take it away.
Yeah, hi, everyone. Like Danny said, my name is Justin Hartland, and currently a flight design engineer with AI Solutions supporting NASA LSP. And today I'll be talking to you all about this project entitled Optimizing Long Duration Park Orbits for Earth Escape Trajectories. So before I dive too deep into it, I want to give kind of a quick 1,000-foot level overview of what I mean by that. So let's say you're designing a mission to Mars. Traditionally, you would launch out of Florida into a nice tight circular park orbit, and from there you would coast for maybe 30 to 60 minutes, but no more than a full revolution, because there's really no reason to hang out any longer. And then at the right time, you would perform your escape burn and be on your way towards Mars. But with some maturity in launch vehicle technology and some kind of interesting advanced ConOps on the horizon, there may be more of a reason to hang out in that park orbit for an extended period of time. So maybe that's several revolutions or several days, several weeks. And there's a couple of things that you might want to do, with that extra time. So today in this project, I'm going to talk about the delta V impacts that are associated with loitering in that long duration park orbit. And then with insight developed from that kind of investigation, we then look at how we can optimize that park orbit to minimize the delta V cost throughout the opportunity. So with that, let's go ahead and get into the project lifespan. So back in the summer of 2023, this project served as my internship project. I just finished my sophomore year of college studying aerospace engineering, so I hadn't gotten into orbital mechanics yet. So this kind of served as my introduction to both astrodynamics, but also like the industry standard programs that we use, kind of like FreeFlyer. So by the end of that summer, we had a nice, tidy study together. It wasn't perfect. It wasn't maybe as complex as it could have been, but I was just starting, so it was a good foundation to work with. And then later in the fall of 2024, I was working part-time with AI Solutions still, and we decided to pick it back up and kind of revamp the analysis with some higher fidelity tools and techniques, and turn the whole thing into a conference paper. So we did just that. Me and Eric Haddix, who was then the team lead for the flight design team at LSP, we wrote this paper up and submitted it to the Rocky Mountain AAS GNC conference in 2025. And last February, I went out there and talked about my results. And today I'm talking to you all about that same paper. So the structure of this presentation will, for the most part, just follow the main sections of that paper. And because of just the nature of the topic, there's some technical terms that I'm going to have to use, and I'll do my best to kind of introduce what those mean as they pop up. So moving on to the motivation to study this project. So like I said, there's some maturity in the launch vehicle and launch vehicle technology that we've seen, but there's also just more players in the game. And with that, more opportunities for missions, right? There's also, more interest in going to cislunar space with CLIPS and with the Artemis campaign, and then even moving on towards interplanetary targets like Mars, right? So because of all of this just stuff going on, there's kind of a need to evolve the mission architecture a bit to accommodate more options, right? So that's where this concept of this long duration park orbit comes into play. So let's say you have a suboptimal insertion from your launch vehicle. You can utilize that extra time you have in the park orbit to overcome those inaccuracies. Maybe you can perform some sort of burn to correct things. But it also enables these more advanced ConOps like on-orbit refueling and spacecraft assembly and whatever else we come up with in the coming years, right? Yeah, this animation's playing here. So that was the traditional mission that we normally see. But before I get to the next one, I also want to say that with the Artemis missions coming up, we already know that the plan will be to perform some sort of on-orbit refueling with vehicles like Starship and eventually New Glenn. So, luckily we can see that this concept will be used in the very near future. So we'll get some more answers pretty soon here. So to help visualize what I mean by these two differences, on the left, the animation that just played is the traditional mission where you launch into your yellow park orbit there. And then at the right time, you perform your impulsive burn or just a regular finite burn. Then you coast to your interplanetary targets. So this alternate idea, the long duration park orbit, you launch into that same yellow park orbit. But instead of burning as soon as you can, you hang out for an extended period of time. In this example, it's just 1 day. And at the right time, you burn, and then you move on towards your targets. Moving on to the scope. So there's two main sections for this study. The first is just studying what the impacts are of loitering in that park orbit on our delta V associated with achieving hyperbolic targets. And then once we understand what those impacts are, we can use the insights developed from that first phase to then look at how we can optimize the park orbit to minimize the delta V cost throughout the opportunity. Now to the methodology. This first slide is just kind of the high-level ConOps here. And in the subsequent slides, I'm going to go ahead and break down each section even further. But to start, I'm not modeling the ascent phase of flight here. We're just starting at park orbit insertion at that blue dot. And then from there, we coast in our park orbit for n number of days. And n will range between 0 up to 20. So for a total of 21 trajectories. After that coast phase, we perform our impulsive burn. And at this point, we've gone hyperbolic. And then we coast to TIP, which stands for target intercept point. And again, I'll break down what all of those things mean here shortly. So for the park orbit, we decided to run with a 500 kilometer by 500 kilometer just circular park orbits. We found that just at that altitude, you're high enough in the atmosphere that you won't be bogged down by drag over a 20-day period. And inclination-wise, we're starting off with a 28.5-degree inclination. That's just your standard, eastward out of Kennedy Space Center inclination. On to the coast phase. So again, we're evaluating a total of 21 trajectories, where the first one is aligned for an ideal departure with no additional loitering. So that resembles just the traditional mission where you launch into your park orbit, and as soon as you can, you burn, and then you're on your way towards whatever your target is. And then after that first trajectory, each subsequent trajectory will start at the same location and time, but remains loitering for roughly an additional day before performing the burn. So I say roughly because maybe after your 24-hour loiter period, maybe you aren't at the right place, the most optimal place to burn. So there may be additional loitering period. Maybe it's 5 minutes, maybe it's 80 minutes, but like some wiggle room to find what the optimal departure time is. And just to kind of bring this home, here's another animation showing these different trajectories. So on the far left here, we have the first trajectory where we're loitering for 0 days additionally. So again, it just resembles your traditional mission. And then next, we loiter for an additional day on top of the original. So how did this play out here? In the meantime, in this park orbit, that's where we're going to be doing your refueling or assembly or whatever it might be. And then after the full day, you go to the optimal time, you burn, and you're on your way. And then again, same thing, but for 2 days, et cetera, all the way up to 20 days. And I'll spare you that animation. You can imagine how long it is. And if there are any questions right now, then now's a good time to bring them up. But if not, we can go ahead and move on.
Yeah, nothing in the chat just yet, Justin.
Okay, cool. Sounds good. Yeah, so next phase here is the impulsive burn. So an impulsive burn is just an instantaneous delta V addition. So rather than a finite burn where you would consider things like thrust and specific impulse of the engines and actually model like a burn duration, we're just using this impulsive burn to simplify the model for now. And the frame that we're referencing that impulsive burn is the VNB frame. So it's just a spacecraft fixed frame. VNB stands for velocity, normal, and binormal. So the x-axis is aligned with spacecraft velocity direction. Y is normal to the orbital plane. Then Z completes the frame. So for an ideal delta V or an ideal burn in general, you want to be burning in the direction of the spacecraft's velocity. But if you need to make some sort of out-of-plane correction, then you can use the out-of-plane component, which would be in the y-axis, but it's famously inefficient to do so. But that will come into play later on. Now for the last phase, the coast to tip. So again, tip stands for target intercept point. It's just an arbitrary location in time and space where the targets are referenced. So essentially, the launch vehicle provider and say NASA LSP, right, been writing up the ICD, they would decide on a certain time and place to reference those targets, and that's what tip is. In this case, I'm just using 10 minutes after the delta V addition. That's when I'm referencing my targets. And the targets themselves, since we're since we're trying to model a mission to Mars, we're going to use hyperbolic targets. So that's made up of C3, RLA, and DLA. C3 you can think of as just speed, and then RLA and DLA are the direction that you're headed towards in space. It's kind of abstract to understand without a visual. So here's a visual. This first one, the red line represents RLA, and you can think of it like longitude. So as RLA changes, we span across the equator from 0 to 360 degrees. And then DLA is like latitude, so we span north and south. And just an example target would look like this, where you span out some RLA, some DLA, and then that's your target, for example. And in the case of this study, these are the targets that I'm running with for each opportunity. So these are just stale Mars mission targets. So just because over time, the relative positions of Earth and Mars are changing, you're going to have a unique set of targets for each day in the opportunity. So RLA and DLA are the blue dots, and C3 is the rising red dot. So for the most part, RLA and DLA are pretty stable. They do change a little bit. But C3, you can see significantly changes over the opportunity, and that will also come into play later on. But just again, to hammer this home, let's say we're working with the first trajectory. We would go to day 1 here. Those values for RLA, DLA, and C3 would be our targets for that trajectory. But then if you move on to day 2, our targets would change slightly to the ones in that day 2 bin, and so on and so forth. Okay, then lastly, for the methodology section, I want to talk about the optimizer. So I decided to use POST2 as my optimizer. That stands for Program to Optimize Simulated Trajectories. And every optimization problem has controls, constraints, and an objective function. So in this case, the controls are the loader duration. So that's the additional little kind of like wiggle room loader duration that we have for each trajectory. Because again, if we loader for a full 24 hours, that may not be the exact point that we want to burn. You may want to, propagate out another 5 minutes or half an hour or whatever. So that extra duration is the control in this case. And then the delta V magnitude. And lastly, the attitude of the satellite at the time of the burn. So effectively the direction that we're applying that delta V in. The constraints are the hyperbolic targets. So again, that's C3, RLA, and DLA. And the objective is to minimize the delta V magnitude. So the optimizer goes in and it changes those three controls a little bit in order to satisfy the constraints. And it tries to find the solution with the minimal delta V magnitude. And once it finds that, that's the optimal solution that we run with. Okay, so now we can get into the results and discussion section. So this first plot are just the ideal delta V values that'll serve as our baseline going forward. So for these, there's no loitering phase. So rather than loitering in that park orbit, we're just launching on the day of the opportunity. So these are all just like standard trajectories that we would normally use. So you can see that the total delta V ranges from around 3.6 kilometers per second, and then increases up to just above 4 kilometers per second by the end. And that increase is driven by the increasing C3 targets that we saw in a couple of slides earlier. Since the C3 target is increasing, the delta V requirement or cost is also going to increase as we kind of dive deeper into the opportunity. And then if you look at the component breakdown, you can see that you have the red and green dashed lines representing the velocity and normal components. For these idle cases, the delta V is made up of purely a component in the velocity direction, no out of plane adjustments needed. Those are just flatlined at 0. So now with that, we can look at the delta V impacts. So this is the delta V associated with loitering in that 28.5-degree park orbit relative to those baseline values. So kind of at a glance, you can see that we have this sinusoidal behavior, this like cyclic behavior. And when we initially, came up with this plot, it was surprising at first. We thought it was just going to be a linear sort of exponential rise as you loiter more and more. But actually, we have this sinusoidal behavior where after a certain amount of time, our delta V impact starts to decrease. So again, that was very surprising initially. So if we start on the far left of this plot with a park orbit duration of 0 days, our delta V impact is 0. And that makes sense because that trajectory is just resembling a traditional mission, no extra loitering, so that makes sense. And then as we loiter for more and more time, we increase up to a peak of just above 2 kilometers per second of impact at a 13-day duration park orbit. And then after that point, we start to decrease again. So now let's look at the component breakdown. You can see that in this case, the out of plane component, it's not dominating, but it's greater than the velocity component. Whereas for our baseline values, they were just 0 the entire time. So that's kind of sounding an alarm to us that there's some sort of alignment problem between the orbital plane and the target itself. That's driving this need for a growing out of plane component. And then of course we decrease again after the 13-day point. So the next plot here is going to show the correlation between this orbital alignment and the total delta V. So the blue line here is the same blue line we saw on the last plot, just total delta V, but the red one is new. And that's sort of representing the alignment between the orbital plane and the hyperbolic targets. So the value is RLA minus the RAN of the park orbit, the inertial RAN of the park orbits. So you can see a pretty clear correlation between delta V and that alignment parameter. If you look at the far left again, for our delta V impact of 0 kilometers per second, that's associated with this orbital alignment term of 0. But then as we loiter more and more up to our peak at 13 days, the total delta V peaks, as does this alignment term, where that gap between the plane and the target is at its maximum. I know it's a bit abstract, So I have another visual in this next slide. This is the same plot, but now we have this visual. So the green line here represents the hyperbolic target, and then the red is the orbit itself. So initially here, this is our first case. You can see that things are nice and aligned. The target lies on the orbital plane, and that corresponds to our minimum delta V impact. But then as we loiter for more and more time, you'll see some evolution going on here. So first of all, you can see the hyperbolic target evolve a little bit. That's just because we have those daily varying targets. But then you can also see the orbit itself rotating and precessing, right? So I'm going to go ahead and scan through here, and you can see this alignment just increasing between the two, or the misalignment rather, increasing until the maximum, which is right around here. And then if I keep going, you'll see that it'll precess back into alignment with that target. So I'll go ahead and run it back again for the beginning. So we're aligned, delta V impact of 0. Then we hit our peak right around here. And then beyond that, we precess back into alignment. And if I were to keep going another 5 or 6 days here, that plane would fully kind of precess back into alignment, and we'd have a lower delta V impact. So that's kind of concludes the first part of the analysis. So we've learned that we do see significant delta V impacts up to over 2 kilometers per second for this 28.5 degree park orbit case. And it's driven by nodal precession, just driving the plane further and further away from the target. But after a point, we start to precess back. So with that knowledge, if we could get the orbital plane to just maintain alignment with the target throughout our whole 20-day period, then we could hypothetically drive down our impacts and minimize everything. So to do that, we want to control the rate at which we're precessing. So to do that, we can use this equation here. Well, again, if we can get the nodal precession rate to match the rate of the RLA target, which comes out to be about 0.167 degrees per day, then we can maintain that alignment for the entirety of the opportunity. So this equation here, there's a lot of assumptions baked into this, so it's not going to be perfect, but it's a good starting point. So if you look at the variables driving nodal precession rate here, the only one that we really have control of is inclination. We can change eccentricity in semi-major axis, but I don't want to. I want to keep my 500 kilometer circular orbit. So inclination is really the only one that we can play with. So if we just do some algebra after plugging that rate in for RAN dot there, we come out with an inclination of about 88.75 degrees. So a polar park orbit rather than the 28.5 degree. And I will say as well, the RLA target rate of change here, the 0.167 degrees per day, is going to be mission dependent. So this particular polar park orbit is not a universal solution, but it works with the set of hyperbolic targets that I'm working with for this case. So again, there's a lot of assumptions baked into that. So to kind of shake all of those out, I went ahead and ran a parametric study. So I essentially ran the same analysis that we saw earlier, but for just a broad range of inclinations, ranging from 86 to 90 degrees, since I know it's going to be some sort of polar park orbit. And I did this analysis in increments of about 0.05 degrees, but I'm only showing the quarter increments here just for clarity. So you can see we kind of get this bowl shape where the maximum delta V for each case decreases in the middle there to its minimum, and then it increases again after that. So it turns out that the optimal inclination is 87.7 degrees, again, for this particular case. So running with the 87.7 degrees, I generated the plots that we saw earlier to check out the delta V impacts. So here they are. We kind of have a bit of a wonky shape, but just look at the y-axis scale here. We're talking meters per second now rather than kilometers per second. So the total delta V there is around 20 meters per second. as opposed to the 2 kilometers per second we saw with the 28.5-degree park orbit. So that's vastly better impact-wise. So if we compare the two now, the solid line here is the 28.5-degree inclination case, and the dashed are that polar 87.7 degree. So let's first look at just total delta V. I mean, it's very obvious that this polar one is much better. So again, the 28.5-degree case rises up to 2.1 kilometers per second or so, but the polar is hovering just above 0. Again, it's about 20 meters per second. And then if we look at that orbital alignment parameter or metric, for the polar case, we're hovering, kind of above and below 0. So that tells us that we're able to maintain alignment between the plane and the targets throughout the duration here. So success, that's good. All right, so to wrap all of this up, after that first investigation, we discovered that the maximum delta V you're looking at, or delta V impact rather, for loitering in that 28.5-degree park orbit is going to be around 2 kilometers per second. And that's driven by nodal precession and this misalignment between the orbital plane and that targets. But then we realized, if we can control that nodal precession rate and maintain alignment as long as we can, and by doing, or we can do that by changing the inclination, then we can minimize our delta V. Then, some analyses going forward, some ways that we can improve, future versions of future versions of this analysis. The main one is that I didn't model the ascent phase at all. And that matters because, I came up with an optimal solution of a polar park orbit, but you can't get into a polar park orbit for free. There's delta V costs associated. So, if you want to get into a 28.5-degree park orbit, launch east out of Florida. And by doing so, you get that additional speed boost from the Earth. But if you want to launch into a polar orbit, let's say south out of Vandenberg, then you aren't getting that speed boost and you're taking a delta V penalty as a result. So the next analysis has to include, that into its conclusion. And there's also some environmental factors that we didn't model. The biggest of which is the propellant boil-off rates. If you take, an ordinary second stage and plop it into a park orbit for 20 days, you can't expect to have the same amount of propellant that you had initially. There's going to be some boil-off. And there are ways to minimize that boil-off, but regardless, we didn't consider it here. And then lastly, it'd be great to develop a procedure for selecting the optimal inclination on a mission-by-mission basis for this sort of thing. So with that, that's all I got. So thank you everyone for tuning in and listening. And I'll hand it off to Chris here to start the Q&A.
Awesome, Justin. Thank you. This was a really great presentation. We're now going to take questions from the chat and also ones that were pre-submitted prior to this presentation. So I'm going to start with the chat. Justin, looks like we've got a handful of questions here from Alan. Alan, thank you for your questions. I'm going to just kind of read these in order, Justin, and I also wrote down the slides that they were related to. So if we want to jump back to slide 2021, around that area, where we were talking about the tip points. So essentially the question from Alan is the tip point of the target that's close to Earth, does that match the optimal path to Mars for the particular burn time?
So again, just to kind of build context again to lead up to this question, the target intercept point is just the reference points for that hyperbolic target. Because if you were to use, let's say, a tip time of 5, or let's say an hour after that burn versus 10 minutes, those values might change a little bit. Now, let me think here. If you change the definition of tip, you can still you'll still be on an optimal path to your interplanetary target. It's just a matter of where you reference them for designing that mission when you're collaborating with the spacecraft team or launch vehicle team. So it's really totally arbitrary how you define tip. No matter where it is, the targets that you come up with at that point are still the optimal way to get to Mars, for example. That's the best. If I didn't quite answer your question, go ahead and put a follow-up in there. But again, tip is totally arbitrary, and no matter where it is, as long as you come up with the right targets at that point, you'll still be on an optimal path to wherever you want to go.
Yeah, no, I think that's a great answer, Justin. And yes, Alan, if you have a follow-up, please post it in the chat, or we could always follow up over email afterwards to talk through it more.
Yeah, totally.
So the second question here was around slide 23, 24, and the question again from Alan was, if you're loitering for 26 days, do you get back to no impact?
So it wouldn't be no impact. So I'm going to go back to this slide here. So if you're on day 26 here and you follow those C3 targets up, your C3 will be much higher than it was on day 1. So for that reason, you're going to need a higher delta V magnitude to satisfy that C3 targets. What will be minimized is the out-of-plane component. So if you were to loiter for 26 days, you would process back into alignment. So there wouldn't be any out-of-plane components. So in a way, it would be minimized, but it wouldn't be optimal. It's still going to be best to burn as soon as you can because of those C3 targets.
Awesome. Great. And then another question here from Alan, if we jump to slide, I think it was around slide 25. The question was, can you optimize even further by adjusting the orbit's RAN prior to that hyperbolic target, or is it more efficient to do it within, or is it more efficient to do it within the hyperbolic target?
Yeah, so again, to kind of build context up, if we look at this slide again here on day 1, the RLA target is around 145 degrees, right? So you want the RAN of the park orbit to also be 145 degrees for those two to be aligned. That's where our orbital alignment parameter showed in that other plot would be 0. So I think about what you might be getting at is if you know your nodal precession rate, and let's say you want to loiter for 2 or 3 days, you can launch into a RAN such that after loitering and processing for 2 or 3 days, the RAN on that day then lines up with your hyperbolic target. So you do have control over that RAN in that way, but you would have to know what your loiter duration is going to be for that to work. If you want to have the freedom to loiter for as long as you want, then that's where it's nice to be in that polar park orbit where you can loiter for 1 day or 20 days and it doesn't matter, you're going to be aligned the entire time. But if you're launching into that 28.5 degree or anything in between, then you can use the fact that you know what the nodal precession rate is going to be and that you know what the hyperbolic target will be at a certain point to process into alignment on a certain day. And you can kind of build that into the mission design. Again, I'm not totally sure if I answered your question there, but hopefully that helped.
Awesome. Thank you, Justin. All right. Looks like we got a few more questions popping up here in the chat.
Yeah, great. It's good to see.
Yeah. No, it's awesome. Appreciate the interactivity here. So the next question, Justin, is, as you mentioned, when you're modeling the ascent or modeling the ascent is critical in order to get an accurate picture of the real benefits of that optimal park orbit. But it's not just delta V alone, right? The loss or performance that you incur by ascending to the polar orbit of the same shape, let's say roughly 500 by 500 kilometers, this results in a decreased payload to that orbit, assuming you were inserting that max payload at 28.5. So
Yeah,
I
I
think that
see
was
what.
more of a statement than a
Yeah,
full
I
question
totally
here. Yeah.
see what he's getting at, and yeah, he'd be right. Like, I'm trying not to consider payload weight or usable propellants or anything like that at SECO 2, for example, in this analysis, because then you're getting vehicle dependent. So if I wanted to rerun this with a Falcon 9 and I know the configuration that I'm going to be using, then you can get into the actual maximized payload weight for those different orbits. But I wanted to keep things genericized, and delta V is a good way to go about it. So yes, you're right. If you're getting into actual mission design, then you're looking at the payload weight effects, not just delta V. So I see what he's getting at there.
Right. And the boil off, as is mentioned too, is worse in a polar orbit, right? Depending on the type of polar orbit, right? Than
Right.
would be compared to that 28.5 degree orbit itself.
Yeah, so I have to admit I'm not well versed when it comes to spacecraft design type stuff. But yeah, if you're in a polar park orbit with an ML tan of 0600 to 1800, that means the orbital plane is going to be normal to the sun vector. So you're just always going to be blasted by the sun, for the entire duration in that particular polar orbit. As opposed to a 28.5 degree orbit where you're going to be eclipsed by the Earth for part of that for each orbit. So I think that's what he's getting at there. But again, that's not my specialty by far. So yeah, that's where it would there's more meat on the bone when it comes to that part of the analysis, where it's the boil off will change based on the orbit you're in, and that kind of thing. So yeah,
no, it's precisely what we're getting at here, which is wonderful.
Yeah.
Thank you, Justin. Great. We do have a few more questions here that were submitted prior. I think we've got enough time to run through them here, which is great. I want to talk about delta V a minute and kind of looking at, why would we look at the impact of delta V in these types of scenarios? And if you considered, let's say, a different factor from delta V, how would you approach the, how would your approach to this analysis change?
Yeah, so that kind of gets into this question just now, where delta V is a great general way to look at things without having to get vehicle dependent. So that's why we chose to go delta V, but the other parameters you would consider would be things like payload weight or propellant fuel weight, or propellant weight rather, that sort of thing. But then you have to know what your stage weights are, the ISP of the fuel, for example. So then that's engine dependent, which is vehicle dependent, so it gets messier. But it would be interesting to do sort of a big trade study with all of the active vehicles. You just need to get somebody who has access to all of those different vehicle parameters and who can potentially publish them. Well, not you wouldn't be able to publish the actual vehicle parameters, but you know what I mean. It'd be an interesting kind of follow-up where then you get vehicle dependent and you see, maybe there's one vehicle that's better at this sort of thing than the others.
Mm-hmm. Do you see a continuation of this research?
Yeah, totally. Definitely. The whole ascent phase addition to the study is very important. And then boil off in the chat as well. So there are certainly some things that I would call this incomplete at the moment. It's a great starting point, but because we didn't consider the DV penalties associated with getting into that polar park orbit, we can't call it complete. So yeah, 100% there will be more analyses done around this.
Sure. When we think about this type of ConOps, do you know if there are any planned missions that are using a similar scenario?
Yeah, the closest thing I can think of are Artemis 3, 4, and 5. We're starting to see some more news about the refueling operations and what's going to be. SpaceX wants to have like a fuel depot kind of in orbit, and then throw up a bunch of starships to refuel, and then with that depot, then refuel HLS, and then get all that payload out to the moon. So, just inherently, you're gonna have to loiter in some sort of geocentric orbits to get that done. So when it comes to on-orbit refueling, definitely, and we're gonna see it pretty soon here, which will be exciting to see. And then when it comes to the assembly stuff, eventually, but nothing right now. Nothing that I can think of. So
awesome, great. Wonderful. I'm taking a look at the chat here. I'm not seeing any other questions. If folks have any other questions, feel free to enter them into the chat here. We can always follow up. Justin can follow up over email if anyone wants to leave their email. We can totally communicate with you. Yeah, afterwards. Thank you, Justin. All right, I'm going to say that wraps up the Q&A portion of this presentation. However, before you go, I do have a couple quick items to talk about to folks. If we can jump to the next slide here, Justin. First of all, I just want to thank everybody again for joining this presentation. If there is interest in learning more about Free Flyer and some of the tools that Justin used to develop these scenarios and this ConOps, definitely don't hesitate to reach out to us. We are always open to booking virtual demonstrations. You can follow us on the QR code here at the top. We also really appreciate the participation of everyone and everyone joining these conversations. We have another webinar in Q1, which we'd love all of you to join. We're going to be hosting in the new year a conversation around designing a horizontal architecture for constellation data processing. That's going to be hosted by our Meridian product lead, Scott Lowe. So definitely RSVP and stick around for that in Q1. And then lastly, don't hesitate to create a Free Flyer account online. If you're interested in taking our certification exam, if you're interested in obtaining a trial of the software for your similar work streams, we always love folks participating and growing their knowledge of these types of flight dynamics and astrodynamics tools in the industry. If Justin, if you could jump to the last slide here. Kind of as a reminder, we're going to be providing the recording to this presentation and the slides to all the attendees in the days ahead. We will also post this webinar presentation on our YouTube page. If anyone has questions, again, feel free. Don't hesitate to reach out to sales@aisolutions.com. You can find us at freeflyer.com. You can call using the number on the screen. And again, just want to thank everyone for joining our Q4 webinar today. This concludes our webinar, and I wish everyone a wonderful rest of their week. And thank you again for participating and joining.